Hey guys, my name is Simon Eisman and I'm a PhD student at the University of Würzburg. And today I'll present to you our work on the cost prediction of serverless functions and workflows. So what are serverless functions? Serverless functions are a cloud offering from cloud providers where you first upload your code segments. And next, you set up a set of triggers which will cause this code to be executed. Triggers can be, for example, HTTP requests or a new message in a queue. Whenever one of those events occurs, your code is executed on demand and with continuous scaling. On the billing side of things, you only pay for the time used with sub-second metering. And this whole process happens without you ever configuring, provisioning a server or thinking about serverless in general. This is where the name serverless comes from. So when we have this pay-per-use model, this is quite enticing, but unfortunately it makes estimating costs very challenging. If we imagine we have a developer that wants to build a workflow, but before he does this, he wants to know how much would it cost to run this workflow. And estimating this is fairly challenging. In general, the cost of a serverless function is calculated from its response time, rounded up to the nearest 100 milliseconds, the size of the function, so the allocated memory or CPU, as well as there's a static overhead for each execution. Additionally, the response time and therefore the cost of a function depends on its input. If you, for example, imagine a function that processes images, the time this function takes to execute will heavily depend on the size of the image. So therefore, if we execute the same function in a different context, this can change its costs. And this fact makes the estimation of costs for workflows very challenging. There are few existing approaches for the cost estimation that mostly focus on individual functions. And what they do is they describe the response time of a serverless function simply by its mean, and they require the user to estimate this response time. So the problem we have is that it's difficult to estimate the expected costs for serverless workflows. And this is the case because the input influences the response time of the function and therefore also influences its costs. And the idea here is to build a predictive model for these workflow costs from production monitoring data. And the benefit this will give us is that this will help guide decision between serverless and traditional hosting. It will enable the comparison of multiple workflow alternatives, and it presents a first step towards fully automated workflow optimization. So this is a broad overview of our proposed approach. On the top, we have the continuous model learning phase, where we have a set of existing serverless functions that are deployed in production already, from which we collect monitoring data. This monitoring data is then fed into our model trainer periodically, and this trainer generates a model to predict the response time distribution of individual functions. Now, if a workflow designer uploads the structure of a workflow he's interested in to our workflow prediction engine, this engine first fetches these individual models from the function model repository. Next, these individual performance models are integrated into a workflow model, and then we use a Monte Carlo simulation to simulate this workflow and thereby estimate its cost. So if we go into a bit more detail here, if we take the following function as an example that takes text segments and translates them to speech, so audio files. If we have a set of text files that all have the same length, for example 250 characters, the function will exhibit a distribution of response times, and also the resulting audio file, the size of this file will vary. So why do we care about this? Why not just take the mean? Here on the right, we have an example function where or function execution time, where we have a mean of 180 milliseconds. And if we would now naively estimate this as 200 milliseconds because of the rounding up to the nearest 100 milliseconds, we would actually underestimate the build time by 30 milliseconds, as you can see by the differently colored intervals. So what this means is that if we want to accurately predict the costs, we have to predict the response time distribution of a function, not just its mean response time. To predict these function response time distributions, we use mixture density networks, which are deep neural networks that parameterize mixture distributions, and a Gaussian mixture distribution or a Gaussian mixture model describes distributions as a linear combination of Gaussian kernels, so a lot of normal distributions. And a Gaussian mixture model can approximate any distribution if it's applied with a sufficient number of kernels. To predict not only the response time distribution of an individual function, but the cost of a serverless workflow, we've adopted the following approach. First, we model the workflow structure, as shown here, for a very simplistic workflow that consists of 3 functions that are executed consecutively with a single input parameter and its distribution. In a second step, we integrate the previously discussed mixture density networks, and each function has one mixture density network that describes its response time, and then one or more mixture density networks that describe its output parameter and their distributions. Next, a flooding algorithm determines the next function for which all input parameter distributions are known. Then, based on a Monte-Carlo simulation, we derive the distribution of any output parameters and the response time of the function. So why do we need a Monte-Carlo simulation here, and why don't we just use the mixture density networks? The mixture density networks are a mapping from a discrete value to a distribution. However, in this scenario, we have a distribution as input and want to describe a distribution as output. Therefore, we use the Monte Carlo simulation to sample the mixture density network and the resulting distribution. These steps are now repeated for any other functions, which in this case is function 2 and function 3. And now that we've determined the response time distribution of all functions, we can calculate the costs for the workflow based on these response time distributions. So when we evaluated this approach, we had 3 distinct questions we wanted to answer. First, can we actually accurately predict the response time and the output parameters of a single serverless function? So basically, do the mixture density networks work in our scenario? The second research question was, can we accurately predict with our proposed approach the costs of a previously unobserved workflow? And the final question we had, what is the time required to build these mixture density networks and to run the workflow cost estimation using the Monte Carlo simulation? To do this, we designed a case study where we had 5 functions. One function that I've shown earlier already that translates text to speech. Then we have a function that changes the audio format from MP3 to WAV of a audio file. Then we have a function that uses a library to detect profanity in any text segments. Then we have a function that can censor audio segments. And finally, we have a function that can compress audio files. All of these file functions we've implemented on Google Cloud, and they're also available. And next, we also had two workflow alternatives based on these functions. And here we have the workflow on the top, where the input text is first converted to speech. Then we convert the resulting MP3 file to a WAV. And in parallel, we detect any profanities in the input text. The detected profanities alongside the MP3 file or WAV file is now fed to the censor function, which censors any detected profanities. And finally, we compress the resulting audio file, and we're finished. And the second workflow is similar. However, we execute this compression step directly after the text-to-speech. In order to orchestrate these workflows, we used Google Cloud Composer, which is a managed solution for Apache Airflow. So, going over our first research question, can we accurately predict the distribution of the response time and the output parameters of a serverless function? Here on the left, we see the observed response times for one of the functions. And then we can see here in green, the normal line describes the mean, and the dashed line, the standard deviation of the first kernel used by the mixture density distribution. As we can see here, this normal distribution is used to fit the bulk of the data. And then we have a secondary kernel with a bit of a lower mean and a broader standard deviation, which the mixture density networks to explain the outliers that are hanging towards the lower end. And since this looks accurate, but it's still hard to tell, here on the right side, we have the observed response time distribution in blue and the predicted response time distribution in red for three different input text lengths, from 300, 600, and 900. And what we can see here, that A, the mixture density network seems to fit the distributions well, and that it accurately depicts that the mean is increasing, but it also accurately characterizes that for a text length of 900, the standard deviation also increases, so the distribution is becoming broader. So following this first visual inspection, we decided to also obtain numerical results. The first question we had here is, what's an error measure we can use? Because now we're dealing with a predicted distribution and an observed distribution. And what we used here is the normalized relative Wasserstein metric, which is pretty much the MAPE, so mean absolute percentage error, but adapted to distributions. So in this table here, all these percentage values are basically the percentage error of our prediction. And for each function, we also ran a hyperparameter optimization in regards to the number of kernels. And in bold, you can always see the kernel count that the hyperparameter optimization selected. And if we go over the values here, they range from 4.5 to 0.4, 0.2, and then there's one outlier with 12.3% error. But in general, we can see that we have a very low prediction error. So we say that we can accurately predict the response time and output parameter distributions of serverless functions. So next, we wanted to investigate the question if we can accurately predict the costs of a previously unobserved workflow. To do so, we measured the cost to execute the workflow 1 and workflow 2 from earlier 5,000 times. In order to do this, we had to allocate 1 day to workflow 1, execute this workflow 5,000 times, and then wait for 4 to 48 hours until the billing reports came in, and then repeat the same process with workflow 2, which was quite cumbersome. And what we see here, when we look at the measured cost between the two workflows, we see that executing workflow 1 costs twice as much as executing workflow 2, even though they implement the same functionality. If we take a look at our predictions or the relative prediction error, we can see that our approach accurately captures this difference with a relative prediction error of 7.8% for the first workflow and 2.2% for the second workflow. Therefore, we conclude that the proposed approach can accurately predict the execution cost of previously unobserved workflows. The third question we wanted to investigate is what's the required time for training and workflow prediction? And this is basically the question. Okay, now that we know that we can actually accurately predict the costs, we want to see if the runtime requirements are actually feasible. On the left, we can see the training time for all models with the hyperparameter optimization turned on. So this means training 10 models for each function. And we can see here that the training time varies between 8 and 20 minutes per function, which for model training is feasible. On the right side, we can see the prediction time with the Monte Carlo simulation. And what we see here, that there's no real difference between the two workflows, with workflow A taking about 16 seconds to predict and workflow B taking about 14 seconds to predict. Therefore, we consider that the time required to use our approach in production is feasible. So if you're interested in replicating the results I've just shown you, or if you want to take a look under the hood and see how any of the individual steps work, we've also published a replication package alongside this paper. It consists of two parts. First, the performance measurement script, which will automatically deploy the functions into your Google Cloud account, perform the performance measurements, and tear them down again. Additionally, we've also published the dataset and analysis scripts we used over the course of this paper. And we've published them as a CodeOcean capsule, which allows you to replicate the analysis side of our paper with a single click. To summarize things, while there's many benefits to cloud computing in general and its pay-per-use model, unfortunately it makes estimating the costs for serverless workflows challenging. Therefore, we've proposed a framework to predict these workflow costs, which at its core uses mixture density networks to predict the response time distribution of serverless functions. And in our evaluation, we've shown that we can accurately predict the distribution of the response time and the output parameters of a serverless function. We've shown that we can accurately predict the cost of previously unobserved workflows, and that the time to do this is within reasonable scope. So thank you for your attention, and I'll see you guys at the virtual ICPE.